Welcome to Pure 3 Vectors. Until now, your coordinate geometry has been locked to a flat, two-dimensional grid, but the real world has 3 dimensions. In this unit, we add a z-axis, giving us the algebraic machinery to model complex 3D space without needing impossible diagrams. In the Cambridge Paper 3 exam, vectors form a highly predictable, self-contained question worth 7 to 10 marks. If you master the core algorithms, this is an incredibly reliable place to score.
Let's look at the foundational tools. You will start by securing the basics. We will translate fluently between column vectors and IJK unit vectors and calculate exact magnitudes. But more importantly, you must learn to separate 2 core concepts. A direction vector describes a pure movement, independent of where you start. A position vector describes an exact location, anchored to a fixed origin. Mixing these up is the #1 reason students drop marks in Paper 3. Always ask yourself, do I need a point or do I need a direction?
Next, we introduce the engine of vector geometry. This is the scalar product, often called the dot product. By multiplying the matching Cartesian components of 2 vectors, you can unlock the exact angle between them. It is also your ultimate proof tool. If the scalar product of 2 non-zero vectors equals 0, you have instantly proved they meet at a perfect right angle. With these tools, we can build paths. In 3 dimensions, we cannot use y equals mx plus c. Instead, we build a path by chaining vectors. We start at the origin and travel along a position vector A to reach the line. Then we add a multiple of a direction vector B to slide along the path. The resultant is R, the position of any point on that infinite line. Once you can build these lines, you will test how they interact. In 2 dimensions, non-parallel lines must cross. But in 3D space, lines can miss each other entirely without being parallel. These are called skew lines. You will set up simultaneous equations to find exact intersection coordinates, prove when lines are skew, and apply the scalar product to find the acute angle where they meet.
By the end of this unit, you will be able to